Okay, this is a quick video over relative volatility. Okay, relative volatility. Volatility. And the symbol for relative volatility is actually just, I believe it's an alpha, and it's A, B for a binary phase system, or binary mixture system, like maybe you have some type of system that's 1 mole A and 1 mole B. So that's for a binary system. And for the relative volatility, it is actually the uh, the I guess I'll say what these terms are. Is actually yi actually represents the components in the vapor phase. So uh, uh, mole fraction of I in vapor, and then the x is the mole fraction. Mole fraction. Whoops. Shun. That goes there as well. Of I in liquid. So with that, we can actually say that the relative volatility is equal to yi, or ya, divided by xa. And that is again divided by yb over xb. If you were to do some, if we were going to say that since it's a binary phase, then x, just want to make sure I get this, xb is actually equal to 1 minus xa, and yb is actually equal to 1 minus ya. If it's a mole fraction, there's only two types of moles, or two types of substance or compounds, then it has to be one minus the other. So then we can plug those back in to get our relative volatilities. So AB is equal to YA over XA, and we're going to plug in this for YB, so that's actually 1 minus YA, or YA divided by 1 minus XA. And that is another way of writing the equation. And actually, if we went back up to this, we can call something a k value. And we're going to say k is equal to yi over xi. So actually this activity, or relative volatility, is actually equal to ka over kb. And that is relative volatility basics. And if you really wanted to go far into it, for a system that's slightly kind of ideal, we can actually say that um, that if route laws applies, we can say that, and if we say the route laws applies, then the relative volatility is actually equal to Ka over Kb, and we can actually say it's just P sat of A over the total pressure, and then it'd also be the P sat, and by sat I mean saturated, of B over the pressure. The pressures cancel out, or the total pressures cancel out each other, so then it's just P sat, or saturated pressure of A, over the saturated pressure of B. And that's how you can, if you don't know the alpha or what the components are, you can use Raoult's law. And this is for I would say low pressures around 1 atm, and it's got to be ideal or nearly ideal behavior. And it varies very little with pressure, so you don't have to worry a lot about the relative volatility. I guess changing with pressure, but if you gotta use a system that has very little pressure change, or that if the pressure did change, how the components acted didn't change very much. And we can just say that's how you can use that. And again, that's for Raoult's law. Raoult's law.